your career, bringing together just this incredibly talented group of chemists from around the world. I've been a few places now, and never have I had such an awesome group of people from all over the globe come together. And you challenged us with important problems, and then you gave us the space to grow. You gave us the environment and the space to just develop as chemists. And so I think we all really, really appreciate that. So thank you, Ian. My group, in the last couple of years, we've spent times doing a number of things, but one of the reactions that I learned to appreciate the strategic importance of in Ian's group was allylic substitution. And it was an important reaction in a lot of the polyketide syntheses that other people were doing, but it was also important in alkaloid synthesis and terpene synthesis, and so just a generally very powerful reaction. Usually, allylic substitution, there was an allylic leaving group, but more recently people have found other pre-oxidized dienes and alkynes and ways of getting into it. But our interest has been into getting into the pi intermediates from CH functionalization. And when we started this chemistry, Christina White's group had spent a lot of time thinking about this, done a lot of chemistry with palladium, a lot of very powerful chemistry. But the palladium chemistry at the time was limited to terminal olefins. It basically still is. Palladium will engage with monosubstituted terminal alkynes. And at the time, the kinds of nucleophiles you could engage were carboxylates, not ethers. Nitrogens needed 2 electron withdrawing groups on it, and then the carbon nucleophiles were malanates and malanite type derivatives. More recently, the palladium chemistry, there's just a beautiful science paper from Christina's group where they could engage secondary amines, but it was still relatively limited, and the alkene scope really is limited to terminal alkenes. So we saw opportunity. We wanted to expand this chemistry. Obviously, if we could get into tri-substituted alkenes, it would really expand the chemistry. And then if we could change the nucleophile scope as well, that would open up opportunities for synthesis. And if we could do all of this, it would also open up challenges in regioselectivity about how you cleave the CH bond, and challenges in enantioselectivity when you were forming the new bonds. And so there were a couple of key insights in the literature that made us think that we could do this. And so the first came from Janine Cossey's group, and she had shown that this rhodium CP star catalyst would cyclize this simple terminal alkene. So it's still a monosubstituted alkene, but what caught our attention was that the nitrogen only had 1 electron withdrawing group on it. So that was a big change in the chemistry and suggested there might be some potential to move forward. And then Ken Tanaka's group, they'd made this really interesting variant on CP star, and they were looking at they were trying to understand the mechanism of Janine's reactions, and they'd done some work making some stoichiometric complexes, and what caught our attention here was obviously the disubstituted alkene, and not just that it was disubstituted, but there was some selectivity where you got the internal pi complex over the terminal ones. And so putting all this together, we felt there was opportunity to develop some catalytic chemistry and hopefully really expand the scope of this allylic CH functionalization. So, given the time frame here, Jacob Berman was the first student to take this on, and sort of immediately found success. And so with these styrene derivatives, we were able to show that indeed you could catalytically aminate them. We got good regioselectivity for these conjugated products. We could introduce amines that only had 1 electron withdrawing group in, so we could start to couple in things like amino acids or whatever amine you wanted to put in. It was Tosyl, it was Boc, it was CBC, it tolerated a lot of the common functional groups. And so it was a really good start. So Jacob got us up and running. And then Taylor in the group, we'd been doing a molecule of the month on eribulin, and we saw these cyclic ethers in it, which are traditionally in the commercial synthesis made with allylic substitution reactions, and so you have to get all that functionality in and carry it through to begin with. And so she looked at this and asked the question, could we just make the ethers? And here this was I think we got lucky. The challenge here is that all of the oxidative CH functionalization conditions, all the metals, all the oxidants, will typically take alcohols up to ketones or aldehydes as well. But kinetically, it turns out that the rhodium catalyst will cleave the CH bond, make the pi-allyl complex more rapidly than it oxidizes the alcohols. And the alcohols would go in, and again, we were able to introduce a range of different alcohols, including a benzyl ether, one that was really susceptible to oxidation, and do this over a range of substrates. So we were feeling pretty good about this chemistry, and starting to think about moving to an enantioselective reaction. And at the time, the mechanism that we were thinking, we were sort of thinking about a CH cleavage, and then we were thinking about a rhodium 3-1 catalytic cycle, and we didn't know if the nucleophile would bind to the metal and then reductively eliminate or attack in an allosphere, but we were definitely thinking rhodium 3-1. But we ran into some problems, and so Jacob went across to Nikolai Kramer's group and had access to all of their beautiful chiral CP ligands. I was trying to make this an enantioselective reaction. And firstly, the reaction didn't work very well, but when he could isolate product, it was like 0% E. Not 2, not 5, but 0, completely racemic. And then Caitlin in the group had been looking at some CC bond-forming reactions with indoles, and she was getting one-to-one mixtures of regioisomers in the reaction. And she kept changing the CP ligand and substituting and doing, and the ratio never, ever, ever changed. So it didn't matter what we did to the metal, didn't matter what we did to the ligand, the products were coming out racemic or one-to-one, and it sort of started to suggest that the metal wasn't involved in the key bond-forming step. So we delved into the mechanism a little bit, and Robert and Daniel, an undergraduate, Robert a postdoc, was teaching Daniel to do the kinetics, and as you'd expect, it's first order in rhodium, it's first order in alkene, it was inhibited by the nitrogen, it was binding off cycle. That didn't tell us much about how the bond was being made, and so Robert started making some complexes, and he made the parallel complex, and he exposed it to the nitrogen nucleophile, and nothing happened, no bond formation. So then we said, okay, the oxidant is in there, maybe, so he actually made the amine substituted rhodium parallel complex. That didn't react. He exposed it to oxidant in case it was oxidatively induced reductive elimination. That didn't make the product. Then he made the acetate, and he exposed that to the oxidant. And he very, very rapidly oxidatively induced the reductive elimination of the allylic acetate. And we took that product, and you show it the amine and either the silver or the rhodium cation, it's just doing an SN1 off cycle. And so no EE, no ability to impact the mechanism at all. This is in fact supported by computation. You see the barrier for reductive elimination at rhodium 3 is quite high, but once you pull this down, take it up to rhodium 4, then you get a competent reaction. So this was what was going on. We were doing the CH functionalization, and what we needed to do was intercept this parallel complex on the metal and eliminate this acetate intermediate that was really causing us problems. So we looked at that and we said, okay, we got to get away from the external oxidant. Let's bring in an aminating reagent that will take that rhodium 3 up to a rhodium 5 nitrate and see what happens. And so Jacob did this. He took the dioxazolones that Sukbuk Chang had developed in the context of sp2 amidation. He put these into the reaction conditions, and sure enough, it amidates, but what was really exciting about this is it completely flipped the regioselectivity. So before we were getting the conjugated products, now we're getting the branch products. We've been able to extend beyond styrene derivatives, do simple alkenes as well. I don't know if I've got it in here, I don't, but we can do di-substituted and tri-substituted, and all of this works. And it really suggested we changed the mechanism, and we're indeed going through this rhodium 5 intermediate. Once we knew that, you could move from dioxazolones to tosyl azides, same mechanism, same branch selectivity. And so this really set us up to start to think again about enantioselectivity. So at the time, Nikolai Kramer has a bunch of these beautiful ligands, and they're great. We'd already used our summer travel money. Jacob couldn't go back, but they take, 10, 12 steps to make, so they became problematic. Tom Rovis and Ward had put CP star into a biotin streptavidin construct. We couldn't do that. And then, truth be told, funding agencies were telling us that if we used other people's catalysts, we weren't innovating enough. So we were challenged to innovate. And what we decided to do was actually start looking at these endenyl complexes. And so endenyl complexes, they coordinate eta5, but they start to slip towards an eta3 coordination to restore a little bit of the aromatic stabilization energy in that benzene ring off the back. And so in organometallic chemistry, this is known as the endenyl effect, and reactions with indene ligands are really accelerated, especially substitution reactions on the metal compared to CP ligands. But we wondered if we could actually decentralize the indene, and use that slippage to induce an electronic asymmetry in the pi-L complex, and then use that to induce enantioselectivity. And there was a hint that this might work from Robert Baker's group at Sydney, and so he had this, again, ugly synthesis to make this complex. But where the eta-3 part of the indene ligand is binding tightly, and it transmits a very strong trans effect through the metal, and the carbon rhodium bond that's trans to that is elongated and weakened compared to the carbon rhodium bond of the other part of the pi-L complex. So we took this, and Caitlin really wanted to simplify it, and so very, very simple indenal ligand. Two steps to make that, one step to put it on the rhodium. It turns out these rhodium 1s were more stable than we realized, and Caitlin was able to pump this down a chiral HPLC, separate the two enantiomers, oxidize it up to the complex, make a small library of these, and straight away, actually, the very first one she made 98 to 2 enantioselectivity. So that was, really, really exciting. She optimized the conditions a little bit, kept the EE high, got the yield up, so here, and we wanted to look a little bit more at this indenal effect, and so we went back to making stoichiometric complexes. Here you see the slight difference in the bond lengths, the slight elongation at the one that's trans to the eta-3 part of the ligand, the slight shortening of the one that's trans to the indenal ligand that's just lifting up a bit. And when we run this reaction catalytically, we do indeed see that it's the longer, weakest carbon rhodium bond that's being emanated. So we think we have a good handle on why this is happening. This reaction is relatively general with respect to the dioxazolones that you can use in here. We can bring in a lot of different amides. And we can also start to desymmetrize or enantioselectively emanate a number of different alkenes. So this one on the bottom right, actually we started looking at as we started to think about this chemistry in the context of synthesis again. And so we had become interested in a broad class of natural products, these CC cross-linked, ripped natural products, ribosomally synthesized, post-translationally modified complexes or compounds, characterized by a carbon-carbon linkage, often between an aromatic ring and the alkyl chain of two residues at the beta position. And we looked at this and we wondered whether we could actually introduce this, build the amino acid with this allylic amidation reaction, and then cleave the terminal olefin to get the carboxylic acid and carry on with these molecules. And so we looked at this in the context of how would the homoallylic stereocenter impact the reaction. It turns out that it's tolerant of it. The inherent selectivity is only in the range of sort of 1.3 to 1, and so the catalyst control it, give us a single diastereomer, and in this case it's the diastereomer that's obviously a model compound, but that we would need for saligentum. So these are really interesting natural products, and there's a whole range of them, and again, by looking at the structures, it's really inspired the reaction development in the group. And so this is another one, and we started wondering about how we would make this, and one that if we could pop open an aziridine, a chiral aziridine, to make at least one of those carbon-carbon bonds. And obviously we've been working with nitrines and thinking about this chemistry a while, and so we wondered if we could actually use our catalysts to make an aziridine enantioselectively. There was some hint of this again, that aziridination was possible, and so Tom Rovis's group had recently published this reaction where they took the terminal alkene and actually made the pyrrolidines, but buried in the SI of this is actually this goes through an aziridine intermediate, and then the acid opens it up and walks it through a whole bunch of hydride shifts to get to this product. But there's an aziridine intermediate. And so we looked at our catalyst, and sure enough, and I think this is, for me, just remarkable reagent control of reaction outcomes. And so up the top is the amidation reaction that we designed and started with. And this is, the dioxazolone is the nitrine reagent. And in this particular case, the CH functionalization, the cleavage by rhodium to make the pi-L complex is fast, and only once as that's happened does the dioxazolone engage and we get that allylic amidation chemistry. We tweak that reagent a little bit, and we use the reagent in the middle, same alkene, same catalyst, and we see none of the allylic amidation product. And here, the rhodium is decomposing the nitrine source first. It's making that rhodium 5 nitrine, and then that's engaging in the aziridination, and we get great enantioselectivity and a decent yield on that reaction as well. And then the real surprise, and Patrick was looking at other possible, he wanted a different protecting group on his aziridine, and he popped in the TROC-based reagent, and then this does another reaction altogether. So now we engage the aromatic ring, likely in some kind of electrophilic aromatic substitution. We really don't know the mechanism of this reaction at all, but it does require some electron density in that ring. If we pull it out, the reaction shuts down. But different reagents, same catalyst, same substrate, completely different reaction outcome again with nice enantioselectivity. So I think we've got a lot of directions to go with this chemistry. It's been a fun place to explore, to develop. We appreciate that the funding agencies pushed us to innovate and really drove some of this chemistry. And once again, I appreciate everything that Ian taught me and allowed me to work with this wonderful group of people. And thank you all for your attention. So.